questions we see regularly from the OpenSearch community is some variation of, I'd love to contribute to the code base, but I'm not sure how to get started. Fortunately, we have Nick Knize here, and he is a Lucene PMC member and committer who knows the OpenSearch codebase as well as anyone. He's here to share his thoughts on how to contribute. Please welcome Dr. Nick Knize.
Thank you so much. Let me get the clicker here. It's good to be here. It's good to see so many people come out to the first ever OpenSearch conference. I got a lot of content to cover here, so we're going to dive right in. I like to take people on a journey typically through my talks, so this talk here is really no different. We're going to discuss three main things. In order to understand how to get started, you got to understand the code base in general. So we're going to talk about the core components. We'll get into a little bit about extensibility and how it works today. We are making some changes to extensibility that are super exciting for the future, but we'll save that for a future unveiling. And then we'll dive into, now that I understand the core components, I understand how to extend it, how do I start developing? And I call this the 3 Bs, branching, building, and benchmarking, all which are equally important. So I like to think of the core as sort of, we call it, you'll hear it thrown around, OpenSearch engine. And it really is kind of an engine. If you're familiar with if you're a gearhead, you're familiar with the 4-stroke engine. This one really is a 5-stroke, where a stroke is sort of, you can consider it as the phase of the engine from intake, compression, combustion, and exhaust. OpenSearch consists of really 5 strokes, right? And the way I constructed this is sort of building it up from the ground up, right? So from the very first atomic component, your field. Your field is really just the smallest piece of data that you ingest into OpenSearch, right? And OpenSearch is, you can consider it basically a distributed Lucene. So at the heart of OpenSearch, the Lucene API is what provides all of the field data and being able to index the field. A collection of fields is what we call a document. So similar to like a JSON. So if you think of an address, it has a number, it has a street name, city, state, and zip. An index is a collection of related documents. And then we have a process by which we can manage all of our indexes and through a common API invoke search over those indexes, and that's what our node is. And then a collection of nodes is how we scale it out, right? So you'll see all these terms throughout the code base, throughout the documentation. These are sort of some formalized definitions to build our foundational knowledge on top of. I'm not going to go through all of the data structures inside of Lucene. There's quite a few. There's about 5 main ones, but a little bit of history of Lucene. If you've been around for a while, it celebrated its 22nd birthday. It's one of the longest running Apache projects. It was initially started as a unstructured text search engine. And at the heart of it was a data structure known as the inverted index. And an inverted index, if you're not familiar with it, is no different than the index in the back of a book. We have a collection of terms that are lexicographically sorted, and then we have a page by which those terms fall on. In Lucene world, we call this the terms dictionary, or our actual terms, and the postings list would be the page numbers. Under the covers, these are 2 different data structures, and they're stored in different files on disk. And that's important because I will talk about that here coming up in a second. So for an example, if I have a single text field called my expression, I define that as type text, and I have 2 documents with these 2 separate sentences. I split those text terms out, put those in the terms dictionary, and then the postings list would be document 1 and 2, or the page number which those terms fall on. Contrast this with a new data structure that we introduced in Lucene 5, which is a block k-dimensional tree structure. It's the first tree structure we finally brought to Lucene. Prior to BKD tree, numerics were all stored inside the inverted index. And we did all this ridiculous bit twiddling logic to try to get numerics to operate in a data structure that was designed for text. So rather than continuing to go down that path, we introduced a true numeric data structure, which now serves all of the numeric data, including geolocation, IP address, and anything that's numerically based that's not text. This is also split out into a collection of files where our internal nodes are nothing but the range of those numeric values. So BKD can handle currently up to 8 dimensions. We're actually expanding this out to possibly give future high dimensional vector type search inside of BKD, but for now it's 8. And those dimensions, we search basically the internal nodes by the ranges of those dimensions. So a single numeric value will be a single range. And then the leaf nodes is where all of the data lives, but it's all organized in such a way that you can access each one of those pieces of data in a logarithmic complexity time. So what's important here is that these two, the internal nodes and the leaf nodes, are stored in separate files as well, a collection of files. Okay, let's take it to the next phase. Now that we understand the individual fields, let's look at what happens with a document when it's presented to OpenSearch. So OpenSearch, based on JSON as an input. So we're going to look at a JSON-based document with 4 fields. 2 of them are text-based and 2 of them are numerics. Granted, one of them is a geolocation, so it's actually a 2-dimensional numeric, and then the other one is a timestamp, which can be broken down into basically a long, right? So the first thing that we're going to do with this is we're going to set up all of our in-memory structures, right? So before we persist this to disk, we do everything on heap in the JVM. And the first phase of this document is to try to fail early. So the first thing we do is we parse out the document. We detect anything that's malformed. This is why in OpenSearch you'll see things like ignore malformed. You can turn that off to say if I have a malformed field, I either want to ignore it and index everything else, or I can fail early and reject the entire document. We also, this is in the life cycle, this is the phase that we analyze that text. So if you look at Lucene analyzers, different language support, breaking those down into terms, removing stop words, things like the that occur common or a, lowercasing analyzers, that all happens right up front after we parse the document. So the idea is here we want to reject and we want to fail as early as possible before we commit anything to disk. So it all goes into memory, and we take our document ID. External document ID 1 becomes an internal Lucene document ID 1, and that's what will go into the postings list. And effectively, internal Lucene document IDs are shared across all of your data structures. And we'll talk about that more in a second. So I now have a second document. I parse out the fields. I analyze them, I ingest them, I put them in a memory buffer. This process continues until that memory buffer gets full, and then what gets invoked is called a flush, an OpenSearch flush, right? The flush phase is where we take everything that was built up, all those data structures that I talked about on the previous 2 slides. They are now built in memory. We are now going to commit those to disk for long-term storage. These go into, I have been mentioning up to this point, multiple files. So if I take my first 2 fields, the first 2 are my text fields. It's going to create in memory an inverted index, which consists of a couple files, a terms dictionary, a postings list, and a few other like scoring factors when we want to actually invoke scoring. These all get persisted into files on disk, and they're prefixed with _0. The extensions vary based on what that file is intended for, and Lucene's got great documentation to talk about what each of those files are if you're interested. I continue this process now for the 2 other fields, the numeric data structures. I now have another set of files, KDD, KDI, and there's a couple other ones there. Those would be the internal nodes and the actual data that tree is representing. And in each one of these files, every single field, shared like single field that's related, so all the text fields go into your terms dictionary postings list, and every single numeric goes into your single BKD files. But now we have a collection of files on disk that represent all the data structures that were conceptually visualized in memory. I then invoke what's called a commit, a Lucene commit. And so when I invoke a Lucene commit, this is when fsync occurs. So everything that I just put inside of a file on disk, which is referenced through my file handlers, when that Lucene commit is invoked, we freeze these files. They now become immutable. You can't change them. They're persisted on disk, and everything coming in the future will follow the same process, creating those files until you finally flush them again. Now I have a collection of files for each one of these phases. What does that mean going forward? Well, a collection of those files, you'll see this word thrown around. The combination of all those files is what we call a segment. So when it's prefixed with _0, _1, _2, that's the incrementing the segment ID number. And we create a metadata file by which we can traverse all of these files for that particular segment. So segment 0, now when I flush, or I should say when I commit segment 1, I'm going to write a new segments file, not a separate segments file, right? I will effectively append onto that segment 0. It will now become segments 1. So as you continue to index data on disk, you'll see one segment file continue to increment _1, _2. That will match the highest number of your segment ID. And this is what we call an OpenSearch index. So the word index is overloaded, Indexes in Lucene are indexing fields inside of BKD, inverted index, but an index inside of OpenSearch is the collection of all those segments and all of those Lucene indices. And you can see this if you just go onto your disk, right? If I go into the index of on a particular node, I will see all the _0, all the _1s continuing as my data goes in. Now, what I don't touch on here are merge policies. Obviously, we don't want all these files continuing to float around, a lot of them that are really small segments, big segments. This is where all of your merge policies come in that try to do a intelligent balancing of trying to merge a lot of small segments into bigger segments. Segment sizes matter, total number of shards matter. We don't touch on all those like cluster sizings in this talk, but this is why. We don't want a whole lot of file handles taking up memory on heap. This is why sizing your cluster matters. All right, let's look at the next phase. So now that we understand what the fields indexes are and what OpenSearch indexes are along with their files and how they're collected on disk, now we need a process, right? And so this is what we call the node. And so if we actually look at under the covers at some of the code, the first two things that happen is we bootstrap a single node and then we start that node. And when we actually start up a node, it's nothing but /OpenSearch. All the configuration is stored off in a set of configuration files, which is inside of a config directory. Typically, you use an environment variable to tell OpenSearch where all these configs live. That'd be log4j, jvm.properties, and then opensearch.yaml. And that has all of your configurations for when a node fires up inside that config directory. But you can override these on the command line, just giving a .E. You can override any one of those at launch of your JVM. So bootstrap and start takes all of that, starts up the process, and the first thing that gets called is indices module.create indices on every node. In this case, we just have a single node. When we call that create indices method is called whether you have an existing index or you create a new index. You can always put a breakpoint inside of create indices, and you can trace what happens with the life cycle of the index. Now, in a single node environment, it's kind of interesting. It's not really interesting because we want to scale to petabyte volume of data, hopefully. But I do get asked the question, does it make sense to have this concept of what we call shards on a single node? Now, a shard is nothing but taking all of that data and splitting it out into smaller windows, right? So if you think statistics, you can do online moving window averages. A shard would be one of those windows, right? And so in this case, we have 3 shards, right? But all of them are going to be primaries. We have no fault tolerance whatsoever because we have a single node. If the node fails, everything's blown up. So there's no need for replicas or any kind of fault tolerance on that single node. But it is useful to shard your data even in a single node because you can take advantage of concurrency. So if you're running a single node, you're just trying things out, we still encourage you to shard your data out so that you can run searches concurrently over those shards in parallel. All right, now we have the cluster. So we've built it up from the fields all the way to the OpenSearch indices. Now we understand what a single node is. Let's look at what happens in a cluster. In a cluster, to form a cluster, you need a minimum of 3 nodes, and this is because there's a cluster manager process, formerly called the master. We now call it cluster manager as of officially 3.0, but it's in the 2.x codebase as well. And we have to use an election process by which we determine which of the 3 nodes will become the manager. And that election process isn't very interesting when you have 2 people that are saying, I'm manager, no, I'm manager. You need a tiebreaker, hence 3 nodes. So we actually run in the code the same thing. We bootstrap each individual node, then each individual node does a start initial join. This is what kicks off all of the logic needed to form what we call discovery, where all the nodes can start discovering each other on the same network. But in each one of those nodes now, we're going to call create indices. So it doesn't matter if you're running single node or multi-node, that create indices method is called. But what's interesting, now that we have a multi-node cluster, we can invoke durability, or I should say fault tolerance, right, through replicas. So each one of those primary shards that you saw now for each one of the indices can have a replica. And you want those replicas to be distributed among your nodes, so if one fails, I can promote another replica as a primary. That's what this is showing you. Under the covers, all it is those collection of Lucene files inside that indices directory, but you'll see inside that directory path, you'll see things like 0 before it. That's shard 0, shard 1. Before that, you'll see a node, an index ID as a UUID. Before that, you'll see a node ID. So the path of your directory really mirrors your cluster. This is why things like snapshot restore, when it was first implemented, was actually implemented very simply. All it did was tar gzipped all those data directories into a compressed zipped up file, transmitted it over the network to another location, unzipped it into the data directory, and boom, you have restore, right? So that was snapshot restore back then. Kind of a poor man's snapshot restore, right, is how that started. And then finally, we want to elect the cluster manager. And this is done through a complex voting process that we could give a whole talk on how that works. But nevertheless, one node gets designated as the cluster manager. That cluster manager's responsibility is to maintain cluster state for the entire cluster. And that cluster state does get shared with all of the other nodes over the network. It gets transmitted over the wire. So it's very important to try to keep your cluster state at a minimum. What's stored in cluster state? We've got pretty good documentation there, but the key takeaway here is don't make your field mappings too large. All of that's stored in cluster state. So if I have thousands of fields, that all gets persisted in cluster state. It's got to be shared out. So if a node fails and a data node gets promoted as a manager, it has the entire field mappings. Okay, so hopefully we've built some foundational knowledge from the field level inside Lucene all the way through OpenSearch, what a cluster looks like and how it's formed. Let's talk about now, I just want to extend it. So that's great, Nick, but all I want to do is write a plugin. Okay, the first thing is documentation. Yeah, we could do better on documentation, and I think we are actually getting better. The first place I encourage you to look is in the Java annotations, and we need help here. So if you're a committer, or you want to become a committer and get your commit bit, help us in the Java documentation by trying to identify parts of the code base that we note as extendable or not, or even experimental. And that's done through these 3 Java annotations. There's OpenSearch Internal, OpenSearch API, and then experimental actually can be related to the other 2. But nevertheless, the internal annotation says, None of the following logic, classes, methods can be extended outside the core, meaning in a third-party plugin, you are not allowed to extend this. Yes, we try to enforce this through final modifiers, class modifiers, and method modifiers, but we need to do better, right? So I encourage you, if you have a PR, some of the things I look at are things like modifiers, right? Because if you open it up as a public API, everybody out there is going to try to, well, people will try to extend it. And sometimes you don't want that, and that's already blown up in our face a couple times. So we try to mark things as internal, even if it doesn't have the private modifier or package protected modifier or package protected. Those things are not allowed to be extended in external plugins. Contrast that with OpenSearch API. These can be and are encouraged to be extended outside the core. And then we have a third one, OpenSearch Experimental. This is to signal to the community that everything I'm writing is not going to guarantee backwards compatibility. So if you are doing encodings or any kind of file formats, you can signal to the community that these file formats could change, or its public-facing API could change in any version without guaranteeing that backwards compatibility with previous versions. This is important for keeping the community moving forward on new advancements without having to be saddled with the burden of backwards compatibility when maybe something's not entirely ready for production. We have another mechanism in place that I'll talk about in a second that you can also use to signal to the community that we're not quite ready for production, but we don't want long-running feature branches. Okay, so now I want to extend it. You really just need 2 things to create a plugin. You need to inherit from the abstract plugin class to signal to OpenSearch that, hey, I'm writing a plugin. And then you need to inherit from or implement an interface from a large collection of interfaces. This isn't all of them. You can see it actually just continues to go off the page. But I've highlighted some key ones here. If you want to implement a REST-based plugin, we have Action Plugin. If you want to override the internal codex or create extensibility inside the actual indexing engine, you can implement the engine plugin and bring your own codec. We also have extensible plugin that says, hey, my plugin can be extended by other people to sort of build up a following on community to things like ML will do this, and a lot of other teams will extend their own plugins. And then the mapper and the search plugin, which is way down on the list, are the 2 areas that you can bring new field types along with new search capability. Now, everything that is an extension inside of OpenSearch is a plugin, but we do kind of have this concept of 2 plugins, 2 types of plugins. Everything's a plugin, but then we also have modules. What's the difference between the two? Plugins are not installed by default. They're optional. You have to manually install them. But what's key for whether it's a plugin or a module is all of them use their own class loaders, and all of them maintain their own security permissions through the Java Security Manager. We do know that that's deprecated, but hey, for the time being, it's still around, and we still rely on it. And then they also have their own library dependencies. I highlighted danger here. If you bring LGPL into your plugin, this will get rejected because of the LGPL's bad licensing for open source community. So we do watch these things. We don't have automation yet. So if you're into DevOps and you want to help write an automated tool to look at transient dependencies and reject LGPL for OpenSearch, come on board. We will gladly take that contribution from you. Modules are installed by default, and they're loaded first before any plugin is loaded. So you'll see things internally like a modules directory. We use modules to help keep the internal functionality modular. We are moving to the Java Jigsaw framework here to also help as well with some of the new features of upcoming Java versions. Now, I mentioned that we have another mechanism to signal to the community that what I'm writing is not ready for production, and this is feature flags. We use them on the team quite a bit. We're using them in segment replication. We're using them in remote storage. We're using them to build core functionality where we can get capabilities into your hands as fast as possible while signaling to you that you may not want to put this in production yet, and hey, we want some feedback from you. So if you want to write something like that, go to the feature flags class, add your feature flag, start wrapping your logic with that feature flag check, and we can enable it or disable it on the command line. Okay, so I mentioned Security Manager. For now, we use it. It's deprecated, yes, but it is very important, right? So for your plugin, it implements its own Security Manager protocol. So you do this by creating a file in your plugin called plugin-security.policy. This is different from the core OpenSearch security.policy because it gets loaded in your own class loader with your plugin. The general rule of thumb or best practice is to lock down everything. I mean, just lock it all down. And then have security exceptions get thrown as you're developing it, and then wrap and do privileged, right? This keeps you thinking security first and making sure that your plugin is at least secure within the greater whole of OpenSearch. All right, so we've talked about the components of OpenSearch. We talked about getting started writing my own plugin. Now let's actually do the development, branching, building, and benchmarking. OpenSearch uses a trickle-down merge or branch technique effectively. And what I mean by that is everything goes into main. None of this is really unique. This is some best practices taken among the open source community. We do this in Lucene. A lot of folks do this. But main is the next major version. It is never guaranteed to be stable. It's always in flight, and it's never guaranteed to always pass your tests. Sometimes you might open a pull request, and you'll see that it fails because something else got merged in that caused a failure. Oopsie, we try to avoid this as much as possible, but it's not perfect. So 3.0 is the development branch in main today. Then you're gonna see the minor releases with a .x. This is the next minor release that is still in flight and not guaranteed to be stable. From there, once we feature freeze, we branch with a concrete minor ID number. So 2.3 gets feature frozen, it gets cut. We now continue to only develop what's going into 2.3, and then when we're ready to release, we don't allow any new features to go in. We only allow bug fixes. So those concrete branches are in-flight bug fix only. And then you backport to whichever one that you want based on a bug fix, based on a feature, and we'll see that here in a second. But before I move on, now that we've branched, you've created sort of your own branch, I understand my feature flags, I understand how to do everything else and the core components of OpenSearch, let's talk about testing. Super important, always neglected. Testing is very important. Every single test in OpenSearch is derived from OpenSearch test case, which in and of itself is derived from Lucene test case. This is important because it provides things like randomization that's already baked in with your random number generators. It gives you a logger with deprecation support to tell you what APIs have been deprecated. And then it also, for new development that's multi-threaded or concurrency, it gives you thread leak detection out of the box, baked into that test case. It is by default a unit test. And so when I create a unit test, the smallest type of test that you want to write pretty much for every contribution, I extend the OpenSearch test case, and then I write my unit tests. Now there's some formatting. You have to start each one of them with test, my test, right? Test, whatever. And that will get rejected or it won't pass through some of the automated check tools that I'll show you in a second. If we build this up, we then look at single node test case. There's OpenSearch single node test case. Now that I've written unit tests, I want to write a test that's going to check this on just my simplest case. One node, I can guarantee, I can even control this down to one segment, right? I can control some of the parameters of how I shard this out in that single test case. That allows me to control my test environment on that single node. I then have building that up into the integration test. This is your multi-node testing. So I will extend OpenSearch integration test, right? And then you have these Java flags, which are scopes, right? So there's two types. There's scope.suite and there's scope.test. Scope.suite says I'm going to spin up a cluster that's going to be shared across all of the tests that I'm about to run. Scope.test says, nope, I'm going to refire up a new cluster every time. Try to avoid scope.test. It's very demanding and it causes all of our checks to run longer and longer and longer. So the best practice here is write your unit tests, write your single node test cases, and then to test it in a multi-node cluster, do a suite scope test. But there's a fourth kind of test. I wrote a plugin that needs to be tested with REST clients. And that is our OpenSearch Client YAML Suite test case. Horrible name. I think we could probably do better there, but it's a YAML test, right? This YAML test, I now write all of my tests using YAML files. And what this simulates is I'm going to spin up a couple REST clients that are going to invoke these REST-based YAML, these REST-based JSON calls, and then I can have baked into my YAML checks to ensure that the way that the test runs and the behavior is actually validated. So go into our YAML tests on OpenSearch and you'll see a lot of files that give you some examples on how to write good YAML tests and also how to skip specific versions of OpenSearch if your client only wants to run against, say, the latest version and nothing before a legacy version. All right, so we've written good tests, we've branched, now let's build. We use the Gradle build structure. In the keynote, they talked a little bit about some of the automation. That's how it's all done. You want to inherit from that automation as best as possible. So no different from if you're developing for Android or any other Gradle project, you need to create a build.gradle, and then you need to inherit that from your plugin or define the OpenSearch plugin. This is where you give it a name, a description, and then you can specify your repositories. And then if you look at some of our core plugins, there's a whole lot of integration setup and configuration, scaffolding. You could do your own backwards compatibility testing. It's really flexible just by changing parameters inside that build.gradle. Once you have that set up, we want to build it. There's two build phases that you're going to use day in and day out if you're contributing or if you're developing your own plugin. The first one is you must run this pretty much before you open your PR, or I should say you should run this. It's /gradlew pre-commit. This is going to run a sequence of about 10 steps that include everything from jar hell, making sure that you're not overriding things on the class path. It will do licensing checks. It will do all of your compilation. And then it will also do a spotless Java check to make sure that your code formatting is good. All that's baked into the Gradle framework, and you get that when you build your Gradle project. The second kind is Gradle check. Gradle check is the full test suite. So it actually runs everything pre-commit does, but then it's also going to run our unit tests, our integration tests, our single node test case, our YAML tests, our REST tests, our smoke tests, and a suite of backwards compatibility tests to ensure that you are compatible, if anything that you're supporting is compatible with previous versions of OpenSearch. Okay, so we've built it, we've written good tests, we're passing our builds. Now benchmarking, which is also probably more neglected than tests, right? So how do we know that we're not regressing OpenSearch? Well, we have two kinds of benchmarks. We have micro benchmarks, which very few people are familiar with, and we have macro benchmarks, which a lot of people are familiar with. The micro benchmarks are probably the easiest for you to run. There's a module inside of OpenSearch called benchmarks, and I can define a series of benchmarks for my plugin or for my contribution that will give me core functionality intended to detect low-level performance regressions really early. And these can get run in the entire suite. and it's run using Gradle. I'll show you how in a second. Then there's macro benchmarks, which are intended to detect the boiling frog, long-running issues, right? So over time, am I long-term regressing my cluster? For a micro benchmark, it's really simple. Inside of the benchmark suite, you can add a new benchmark, and then there's a series of Java annotations where I define how many threads I want to run. So fork, how many iterations I need in warm-up to warm up my cluster or warm up my tests. What units of measurement am I going to use? How many internal iterations and how many measurement iterations am I going to use? And then what kind of units am I going to use? And then what is at state scope benchmark is how I define that this is a benchmark. From there, I use the at param to define my benchmark parameters. I use at setup to do all of my initial setup of the benchmark. And then I use at benchmark to define that this is the benchmark test case that I'm going to run. And you can use other things like at threads to say I want this to run in 4 threads with this many iterations. Now when I run it, I do Gradle w-p benchmarks run. And that's going to spit out micro benchmarks for all of the tests that I just ran. And it will give me all my measurements so I can detect performance or memory leaks. I can just detect computation regressions and just look over time as this continues to run, what's the performance look like for that internal implementation. And then I can also override any one of those parameters on the command line just using the Gradle --args parameter. And that will tweak on the fly through command line what gets passed into that benchmark. Macro benchmarking. Macro benchmarking is what we released not all that long ago. It's called OpenSearch benchmarks. So I have to do a little bit more work here. First, I have to go out and I have to install the benchmarking by using pip install. But once I have it installed, I run OpenSearch benchmark, execute tests, and I can specify the version that I want to run these benchmarks against. What this is going to do is it's going to spin up a full OpenSearch cluster as opposed to micro benchmarks, which are just going to run, say, on that single node type scenario. I then specify a workload. In this example here is geonames. How do I know what kind of workloads that OpenSearch provides? Well, we have a repository. Inside of OpenSearch-project, there's an OpenSearch benchmark workloads repository that contains a whole lot of workloads that you can run. Anything from Stack Overflow data, logs data, and we take contributions from folks, bringing in new kinds of benchmarks for things that need like deep replicas or append-only log use cases. We can add those benchmark tools there for the community to use. Okay, so let's see, we talked about a lot. We talked about the foundation of OpenSearch. We talked about how to build extensions. We talked about how to test them, how to actually benchmark them. And now I want to contribute. So in the contribution, as I mentioned, the trickle down, we open everything against the main branch. So when you open your PR, open against the main branch, and then we have a set of labels that we apply where you have to specify what you want to backport your PR to. And so in this case, I show an example, backport 2x, backport 2.0, but it's intended for 3.0, right? So you add your target version, and then you add your backport labels. And this is important because we have automation built in that when you designate that backport label, a trigger bot will be fired off to backport for you to the proper minor branch. So you don't have to open up all the follow-on PRs. This was a huge contribution by the team, so whoever helped out in developing that, huge thank you. Okay, so where do I get started? And this is where I want to leave you. Go on out to OpenSearch-project, go to any one of the repositories, and we should have this flag called Good First Issue. You can look for Good First Issue. There's also another one called Low Hanging Fruit. We could do better actually keeping this up to date, but there's some good ones out there that you can get started with. And then also, I think Charlotte will be here later on today to talk about this, the roadmap. Where's OpenSearch going? How can I help contribute to some of these new features? And where do I get started? If you don't see an issue already for something that you're interested in, open it up. We'll help you triage it. We'll help find a version for you, and we'll help collaborate. And I'll be here for a short bit, so if you have any other questions, I'm happy to talk. Thank you.